Hello, this is Mark Anderson for Kellogg Community College, and today we are going to be doing a review of Unit 3's Unit 3 in our statistics class. We are going to look at some definitions and get through some confidence intervals down at the bottom of the page. First, we're going to look at some vocabulary. You should know what a type 1, and type 2 error is. In fact, what we are doing with our hypothesis testing in this book is we are either going to be 90, 95, or 99% confident that we are not making a type 1 error, and a type 1 error is when we reject the null hypothesis. I'm going to put this in all caps. When we reject the null hypothesis, and that's H sub 0 for the null hypothesis, when it is true. I'm going to put this in all caps. These are the words to really remember here. The type 1 error is when we reject the null hypothesis when the null hypothesis is true. A type 2 error is when we do not reject. Notice the difference here. The null hypothesis when it is false. This is if we know, for example, the null hypothesis is right and the null hypothesis is saying nothing is happening. People can say that, oh, you're making a type 1 error if you're saying something is happening when something isn't happening. So let's say, for example, there's a drug at a company. You may be working for a drug company, and you really want this drug to do something when someone takes it, but the null hypothesis person is saying, no, the drug doesn't actually do anything if you take it, and it doesn't move the needle at all. You can't say that the alternative to that, which is the drug is doing something, is true. So you're making a type 1 error when you're rushing, like let's say you have a drug or a chemical and you really want it to do something, but it just doesn't. The data and statistics, when you run that drug with controlled samples and you see that it's just not moving the needle far enough to be 90, 95, or 99% positive that a type 1 error is happening, that's when you're going to make a type 1 error, when you want something to happen but it just isn't happening. And this, on the other side, as the book will explain, it's very difficult to show if a type 2 is happening. That's when you do not reject the null hypothesis when it's false. This would be if, like, someone says, oh, nothing's happening, but you're going, yes, it does, it is happening, it's happening. Someone will then claim that the type 2 error is when you just can't, you're just basically saying, no, there's nothing happening, but that's absolutely false to a situation. But I would check out the book because it has a really nice explanation about why type 2 errors are so hard to fix. But the type 1 errors are easy to identify because we can measure the needle moving, and that is going to be done when you do a 5-part normal hypothesis test. So the first part of that is going to be to state the null and alternative hypothesis, and you're going to see in the subsequent videos I'm going to make is that you will see all 5 of these steps illustrated. So the first thing is to state your null and alternative, and the second step is to find the critical value. And I'm going to be, especially on my tests, I'm going to accept the answer, not like a rounded or close enough or something your calculator spat out. You're going to have to use your table and figure that out based on Z versus T scores, and just really like watch how you do the work there to find that critical value. The third step that you're going to do is then run the test value, and the test value are going to be on your formula sheets. And it's going to basically be on whether you have 1 or 2 variables, if it's a before and after situation with 2 variables, independent versus dependent, and we're going to make a whole flow chart based on that just to kind of help you, decide on which one you're going to choose to do. Step 4 is you're going to draw a picture, and drawing the picture is going to be nice because you're then going to have to put your learning where you can see it, so you can draw whether it's a left tail, right tail, or a 2-tail hypothesis test. You can mark your critical value, you can mark where your test value is to see if you're actually in the critical region. And once you do all of those 4 things, you're going to make a conclusion, and the conclusion is going to be a sentence with at least 1 inequality in there, and that's going to show me what you're looking at and show me why you've chosen the way you did. If you're going to do a p-test, actually steps 1 and is the same. You're going to talk about your null and alternative hypothesis. Step 2, instead of finding the critical value, you're going to run the test value. And then when you find your test value, because it's going to be a z-score or t-score, then what you do is you're going to compare that z or t-score to the chart. And I have been teaching specifically about p-tests that have an alpha at 5%. I don't think I assigned anything that didn't have a 5%, and if they were very rare, few and far between. But after you check that, what you should do is just basically ask yourself about, is it below 5%? Is your data within, because since we have an alpha fixed at 5% for most all of these problems that we did with p-tests, we had to see, well, is my data, in that upper 5% if you're doing right tail, or lower 5% if you're doing, the left tail, and then, double your percentage when you do two tail. And then number 5 is going to be make your conclusion. Alright, so that's what you do, the difference between a p-test and a t-test. Notice there's no picture. You're going to basically run the test in option 2 instead of option 3, and then we're going to basically look when you take your value and run it into the chart. You can then check to see, if it's under that 5% or not. And there's specific videos that go through these p-tests in section 8.2 and 8.3 that you can watch again if you have questions. So what we're going to do now is ask one more question about p-tests before we move on to the confidence intervals here. And it says basically, what is the threshold for p-tests to reject, not reject the null hypothesis? And just because we have chosen 5% for our lecture and for many of the problems in the book, if not all of them, that is going to be where you're going to have your threshold for problems to be rejected or not rejected. So if they're under 5%, or if they're above 95% on the top end of the chart, then you're going to reject the null hypothesis. There's, this group is clearly within the top or bottom 5%, or, for two-tail, we would double the percentage. Oh, I just wrote T-O, ouch, T-O, two-tail. Wow, two-tail. So the two-tail test right there is going to be what we do when we double the percentage, because we have to take into account that each side of the tail is half the data. So by doubling it, we make sure that we have compensated for that. All right, so finally, so for our two confidence intervals here, you'll notice that these two confidence interval problems have two different averages there. And what we're trying to see is if the averages, if we subtracted them, would it be possible that there'd be no difference? So is it possible that the two averages subtracted could be 0? And that is what we're going to check here. We're going to check to see if both of these numbers are positive, both of these numbers are negative, or one's positive, one's negative. Now, what that means is that if we have two negative numbers or two positive numbers, then there's no way that subtracting these two averages could be 0. And if that's the case, then we would reject the null hypothesis. Because if the differences are never going to be 0 between these two groups, like the two groups are always going to elicit a positive or negative number, then they are going to not ever be the same. Because that's what we're doing when we look at two different groups. We're trying to see if the two different groups are in fact different. And if they are different, then their averages will be different when we compensate for their standard deviation and our error. So the formula is going to be our two averages subtracted by each other, so x bar sub 1 minus x bar sub 2, and we can actually do these in any order, but I think I will just choose group 1 minus group 2. This is 123.5 minus 126.2. Alright, so I'm going to put that in parentheses here, and I'm going to go minus, and that's going, again, I'm using the formula from the formula sheet, and then we're going to get our z alpha divided by 2. Now I'm noticing this is a 95% confidence interval, and these groups are greater than or equal to 30, and since that's the case, I'm going to use my z chart. since I have a 95% confidence interval, my alpha is going to be 5%. And since I have two tail, because this is a confidence interval, I'm going to have a left and right tail, I'm going to get my alpha and divide it by 2, which instead of this being 5%, it's going to be 2.5%. And so that means I'm going to look up 0.0250, and I'm going to also look up 0.9750 for both sides of my critical values here. And that critical value right there, that z alpha divided by 2, is going to be 1.96. And that's the number that's closest to the 0.0250. And in the case of a tie, I always go furthest away from 0. So if I have a choice between negative 1.96 and negative 1.95, I would choose negative 1.96. And then I would multiply this by, and again from the formula, I would multiply this by my 19.9 squared divided by the sample size, which is 70, plus 15.0, sorry, there's no decimal there, 15 squared divided by 60. So this is my left-hand side of the mu1 minus mu2, and the right-hand side is going to be all this again with one small difference. The difference is that it's going to be a plus instead of a minus. And in fact, what I can do is kind of like shortcut my work a little bit, because since I know the right-hand side is this entire thing with a plus instead of a minus, I'm just going to do parts of this at a time. I'm going to subtract these two, which gives me negative 2.7. And then I'm going to take negative 1.96 and multiply it by the square root of this fraction plus this fraction. Now, I'm not going to go through the calculator and show you that. If you have specific questions on the technology, please email me or work with me in class and I can help you with that. But we did ample work in class, so this is going to be negative 6.01. And if I subtract these two numbers, I get a negative 8.71 for my lower part of my confidence interval. I am 95% confidence interval that the difference between the two groups is going to be either negative 8.71, or on the other side, if I just did the entire equation over again, but in this case with a plus instead of a minus, then I just add up this side here, which gives me 3.31. This means that I am 95% confident that the difference between these two groups is either going to be a negative 8.71 and a positive 3.31. This means, now you just got your answer and you might be just like, oh sweet, I'm just going to move on, but let's think about what this means. It means that the difference between these two groups could in fact be 0. Like 0 is between these two numbers. And since 0 is a possibility, we will not reject the null hypothesis, because the null hypothesis says that, hey, that mu1 is equal to mu2. And if mu1 is equal to mu2 in this null hypothesis, then that means that, hey, we have the possibility that subtracting these two will give me 0, right? Because if mu1 is equal to mu2, then this minus this is going to be 0. And since 0 is a possibility, we would not reject the null hypothesis. But if both of these numbers were negative, or both of these numbers were positive, we would say, oh man, then there's no chance that mu1 is equal to mu0, because the differences are going to be not 0. Like both negative or both positive means that there's always going to be one group that's going to be lower or one group that's going to be higher than the other. Now, I just went through that explanation, and there it is in problem number 7 here. So let's actually do the problem again. We'll do it a little bit faster here, but notice in this case, the sample size here is less than 30, and just because I wanted to make it pretty straightforward and not get into all the minutia about groups below 30 being possibly normally distributed, I just wanted to say, hey, we're just going to use a t-chart if we're going to go below 30, and a z-chart if we're 30 and above. So here is we have mu1 minus mu2, so it's the same formula as before, except that instead of z-chart, you're using a t. So here's our two x bars right here being subtracted, and you could again subtract them in any order. It's just that you should, again, I'm going to just go in this order here and see where this takes me. I'm then going to go minus, and I'm going to look up on my t-chart my degrees of freedom. Now the question is like, what do I do for degrees of freedom? Degrees of freedom is n minus 1, and we will always choose the smaller sample size, because what that will do is it will give me, it actually hurts the statistician. It gives me a larger value here for my t alpha divided by 2, and when I get a larger value here, and if you look at the chart at 15 degrees of freedom for 99% two-tail, because confidence intervals are two-tail, this would give you 2.947 based on the chart that I'm supplying you. So this chart right here, this number is actually bigger if you use the n of 16. If you use the n of 17, which would be then 16 degrees of freedom, this would be a smaller number, and our confidence interval would be smaller. You're really not, you're supposed to use the bigger number, and that is better for the statistician. It's better to show that you were trying to be honest. And so, yeah, always choose the smaller sample size, because it's going to give us a larger confidence interval. All right, so with that in mind, here we go. Next, multiplied to that is the standard deviation squared again, divided by the square root of, the sample size under the square root. And then we're going to have 179.4, and we're going to square that and divide it by 16. All right, now again, that's on the left-hand side of mu1 minus mu2, and the right side is going to be this entire equation again with a plus. So I'm going to shortcut my work by doing one side only with the minus, and then I'll compute all of this in one string. And again, if you have technical difficulties and you can't get 176.3, I strongly recommend that you use parentheses more, like 2.947 square root. It's going to give you a parenthesis. If not, put a parenthesis of 163.2 squared divided by 17, close it off, then add, and then start another parenthesis. The 179.4 squared divided by 16, close it off, and close it off again, because you've got to make sure that all of this is inside of that square root. So if you can't get 176.3 or something close to it, you may want to check your technology and see if you did things slower, like if you just computed each of these fractions, then added them up, then took the square root, then multiplied by negative 2.947. See if you can get close to 176.3. All right, so if I subtract these two, it gives me negative 61.6. And if I do the other side, which will be the plus of that, so I can put the plus minus there. You can see how the formulas on some sheets or some videos I use plus minus instead of listing both sides of this equation, but it gives me 291. Now you can definitely see that between the 661.6 and the 291, you can see that 0 is a possible answer between that, because you're going to have apparently between these two averages, at the worst a difference of negative 61.6, and at the best a difference of 291. We are definitely not going to reject the null hypothesis, because 0 is a possibility. And I'll repeat it again. The null hypothesis is asking, is mu1 equal to mu2? And that is possible if 0 is the difference between these two, which is what this is. So if these were both positive or both negative, we would say, hey, there's a possibility that, or there's no way that they can be the same, so we'll reject. But since 0 is between a negative and a positive, we will not reject. All right, thank you for watching.